This is Unit 8, Area and Solids. Preview video 8.3, Area and Probability. Sit up and inhale. Deep breath, hold. Slowly exhale. Stretch yourself taller. Ready? Inhale. Hold. Exhale. You are now looking at 8.3. You're going to need a calculator handy and some colors. Let's do a quick recap of your previous lesson here. It says below is a regular pentagon. Pentagon, 5 sides. Regular, all sides equal. The length of each side is 10 centimeters. Find the area of the regular polygon. The first thing, of course, is you simply want to write the equation for area of a regular polygon. Area equals pa over 2. So you come here and we trace our perimeter. We have our perimeter. Our perimeter is 50. Of course, 5 times 10. We are missing our apothem, which is right here. We need that. Perimeter times apothem over 2. So we need that apothem. So we're stuck. Not exactly. Wherever there's a right angle, you always want to create a right triangle. Wherever there's a right angle, you want to look for or make a right triangle. We're going to do that by drawing in a radius. And if this whole side is 10, this is 5. We want x. Now you're back to have, need, do. So right here, we need an angle to work with. Obviously, we have a side length, so we're going to make our circle. We go all the way around our pizza slices, and we see that if one pizza slice is simply going to be 360 divided by 5. So we get this is 72, which means this angle right here is half of 72, 36. Let me pull it down. It's a little bit easier to work with. We have 36. We have 5. We want the apothem. That's what we're missing. So taking a look here from the 36, this is opposite. This is adjacent. It is an OA combo. That's TOA. Tangent of theta over 1 equals opposite over adjacent. Tangent 36 equals 5 over x. Cross multiply. So our x, which is our apothem, which is what we need here, is going to equal 5 divided by the tan of 36. 5 divided by the tan of 36. And that's going to give you your apothem, which we are looking for right here. So your calculator, 5 divided by tan, 36. My calculator is going to look like this. 5 divided by 36 tan equals, whoops, hang on, 5 divided by 36 tan. Oops, I'm in radians. That's my problem. Got it. Degrees. Let's try that one more time. 5 divided by 36 tangent equals, there it is. We're going to round to the first decimal. 6.9 is our apothem. And now To get the full area, we're going to do 50 times our apothem, 6.9, divided by 2, and we get area equals 172.5. Let's check for units. Our units are up here. Centimeters squared. I'd like you to take a moment and I'd like you to star which one of these steps might you have forgotten if you were completely on your own. Is it the circle pie slice angles? Is it the fact that you had to do SOHCAHTOA? Is it the step where you had to cross multiply and figure out you're dividing and not timesing? Which one of these steps, if you were completely by your own, I'd like you to star which step might have you forgotten on your own. We're going to talk about area of regular and irregular, also known as composite shapes, area of composite shapes. So there's a couple shapes that we've already discussed. Normal shapes are just normal shapes. Triangles, circles, trapezoids, they're a single shape, but they're not regular. Triangles, circles, trapezoids. Then you have your regular shapes where all the sides and angles are equal. Both of these would be considered regular. Regular, all sides or angles equal. So we have normal shapes and regular shapes. Then we have what's called composite shapes. Composite shapes are shapes that are made up of other shapes. For example, in this entire singular shape, if you were to see it as a singular shape, you have a semicircle and, of course, a triangle. So the composite shape is made up of multiple shapes. Here, of course, we have two different rectangles. So composite shapes are made up of other shapes put together. So composite shapes, irregular shapes, are combinations of multiple normal or regular shapes. Okay, we need to learn to see these shapes in two different ways, both a breakdown of smaller shapes and then using something also called negative space. So we're going to find the area of the shape below, and we're going to visualize it as two separate rectangles. There's a couple ways you can visualize it. You can visualize it horizontally, if you will, or you can visualize it vertically. Both of these methods work just fine, but it's made up of two different rectangles. I'm going to go ahead and use the horizontal method here. So we're trying to find the area of the entire shape, and the way we're going to do that is we're going to find the area of these two rectangles. So it's good to break them down. This area, physically trace always. I trace this here. My length is 6. I trace this here with this 2. Of course, that area is 2 feet, 12 feet squared. Always physically trace. Watch here, watch very carefully. Length, width. Just trace that a couple times. Trace that a couple times. Be very careful here. Our area here, our length is 3. Now go like that with your finger. Be very careful. That is not 5. physically trace. That whole side is 5. Get your finger on the paper, friends, finger pinch. Whole side is 5. Then this little piece is 2. So now you should be able to feel that this piece, which is our width, is 5 minus 2, which is 3. So the area of this is 9 feet squared. So the area of the entire irregular shape, of course, is 12 plus 9, 21 feet squared. So that's one way to do composite shapes, is to visualize it as the combination of smaller pieces. There's also a shortcut called negative space. So another way you could visualize the area here, the orange area, is by first finding the area of this larger outer rectangle, the area of that length, 6, width times 5. So that's 30 feet squared. And then to take out this empty space area. And if you watch carefully that empty space area, if this whole thing is 6, and from here to here is 3, that's 3 this way. If this whole thing is 5 going this way, and this little piece is 2, then this is 3. So my empty space here is 9 feet squared. So to get the orange, you simply subtract. And that gets you your composite space, which in this case is the orange. Notice it's the exact same thing. So composite space you can do by smaller spaces added up, or larger space, negative space, subtract. Let's do another example of a composite shape. I think it's important when you do composite shapes to identify which one is easier. So here, this one would be a little tricky because I can't use a regular circle as my larger space. And I can't exactly use a rectangle because I have all these like curved spaces. So I'm going to use the smaller added to the larger. So always identify first your shapes and then write the appropriate equations for each of these. So I'm going to be adding the area of a half circle added to the area of a triangle. Area of a half circle, of course, is going to be pi r squared over 2. Area of my triangle is base times height over 2. So let's focus in here. The easier one here is our semicircle. So our radius, go like that. We need that. Swing it around. Same thing there. You're like, there's nothing there. Well, look at what you have. If you have all 3 sides equal, that makes this edge also 36, which makes this radius half of 36, which is 18. So we just found our radius is 18. So it's 18 squared times pi over 2. That's going to get our semicircle. 18 pi, 18 squared times pi over 2. So 18 squared times pi divided by 2, 508.9. So I have here 508.9 units squared. That's this one, 508.9 units squared. Now your triangle is base times height over 2. We have the base. The base is 36. The problem is we're missing the height here. We're missing the height. We're like, what could we do with that? Well, how could we find that height? Look very carefully. 3 equal sides, 3 equal angles, which means that's 60. So I have here an unknown side. I'm pulling this right triangle out. Where there's a right angle, you should be hunting for a right triangle. That's 18. That's 60. SOHCAHTOA, once again. This is opposite, this is adjacent. I got an OA combo, that's tangent. So the tangent of angle 60 is our opposite, which is our unknown, times our adjacent, which is 18. So x will equal tan 60 times 18. X equals tan 60 times 18. So 60 tan times 18. Take it to the tens place. Oops, I think I divided there. Let's do that again. 60 tan times 18. There it is, 31.2. So our height is 31.2. So to get that triangle, we're going to do 36 base times our height, 31.2 over 2. It's going to get us that area of the triangle. So 31.2, I'm just going to leave it there, times our base, which is 36. I'm going to divide by 2, and I get 561.2. So our composite shape here, 561.2, is going to be 508.9 plus 561.2. And I get 1,070.1. Units squared. Now ask yourself, in this entire process, if you had to do this completely on your own, I'd like you to circle which one of the steps might you have overlooked on your own. And if you didn't, that's fine. Would you have overlooked remembering to divide by 2 here? Would you have overlooked the fact that you needed the height? Would you have overlooked the fact that it's tangent versus sine or cosine? Would you even thought of the fact that you needed to use SOHCAHTOA? Would you have overlooked the necessity of adding them? So I'd like you to circle which one of the steps might you have overlooked on your own. Now that we can do composite shapes, we're going to talk about geometric probability. Geometric probability. The best way to introduce geometric probability is to simply do a problem involving geometric probability. Geometric probability is the probability involving area and volume. It's the probability that would involve potentially area and volume. Read this out loud, finger on your paper. Find the area of the shaded region. Shaded. That's in this, that's all of this area, shaded. Find the area. The inside shape is a rhombus. That's important. We're going to go like this. It's a rhombus. So, rhombus. The vertex is 1.5 centimeters from the side. So each vertex go in like this. It's 1.5 cm, 1.5 cm, 1.5 cm, 1.5 cm. We want to find the area of the shaded. Now this is a negative space. To find the area of the shaded region, we're going to make ourselves an equation. We're going to find the area of the larger outer rectangle and then we're going to find the area of the inner rhombus. And then to get the shaded region, we're going to use what's called negative space, which means we're going to subtract the rhombus from the rectangle. And that would give us our shaded region, as you can see. Now, let's write our equations down. Area of a rectangle, area equals length times width. Rhombus, area equals diagonal times diagonal over 2. Diagonal times diagonal over 2. Let's see what we have here. Right here, our length is 10, our width is 6. So we have all that information. Our length is 10, our width is 6. So the area, of course, is going to be 60 cm squared. In the rhombus, take a very close look here. We want this diagonal. Now take your finger and go all the way across. That is 10. We need this diagonal here, so I want you to take your fingers, go like this, say 10 centimeters. Do this with me, finger pinch. Now ready? Go in 1.5, go in 1.5. Both of these are 1.5, which means we are going in 3 units total, which means this length here is going to be 10 minus 3. So that means our one diagonal is 7 units. Our other diagonal between my fingers is 6, and I go in 1.5, 1.5, so I'm losing 3, which means 6 minus 3 between my fingers. I get the diagonal of 6 minus 3. I get my other diagonal is 3. So we're doing 60 minus, and of course that's going to be 21 divided by 2, which is 10.5. So my shaded region is 60 minus 10, 50. And then the 0.5 is going to be 49.5 units squared. That is the area of my shaded region. It's negative space. Now, here is a secondary question. This is related to probability. It says right here, what is the percent probability that a point will be in the shaded region compared to the entire rectangle? So this is probability related to area. So what this question is asking is, what is the possibility that any point is going to land in the shaded region compared to the entire rectangle? What is the probability? And percent probability is a very simple concept. It's simply the area of the potential divided by the area of the whole. And in this case, the area of our potential is the shaded region versus the area of the entire rectangle, which is this. And you simply divide. So we do 49.5, 49.5 divided by 60. And there's an approximate 83%, 0.82 is 83%. So there is an 83% probability that a point landing inside the rectangle will actually end up landing in that shaded region only, which makes sense. There's more shaded region than not. Let's try another problem. This one we'll do together. The next one you're going to do on your own. Below is a circle. So let's just kind of get our bearings here. We have a circle. And the circle is inscribed in a regular hexagon. The radius of the circle is 10 centimeters. So the radius of the circle, center to edge, is 10 cm. Now, I could have drawn it anywhere. Okay, there's a reason why I particularly drew it, because I drew it in such a way that the radius of the circle is also something of that hexagon. You'll see that in a minute. There's two steps. We want to find the area of the shaded region, which is this shaded region, and the area of the shaded region, and then the percent probability that a point lies within the shaded region, so a point coming compared to the entire hexagon. What is the probability that these points will possibly land within the shaded region compared to the entire hexagon? Step one, shaded region. We make what's called an icon equation. Our icon equation is this. To get the shaded region, it's going to be hexagon minus, so if we find the area of the hexagon and we find the area of the circle, all we have to do to get the shaded region is subtract the circle, from the hexagon. Subtract that circle from the hexagon, and we will end up with the shaded region. It's getting a little messy. All right, so we write our equations. Area of this is Let's start with the easy one. We were given the radius of the circle. Let me clean this up a bit. Okay, there's the radius of our circle, 10. So we're going to come over here. That's 10 squared times pi. You should already know that's going to be approximately 31.4, but I'll just show you on a calculator just for giggles. All right, so that's going to be 10 times 10, which of course is 100, times pi, and we get 314.2 approximately. That's going to be the area of our circle, 314.2 units squared. Now, coming to the hexagon, we need the perimeter. Problem is, we don't have the perimeter. That's our unknown, but we do have our apothem. Our apothem is 10. We need our perimeter. So now, back to the idea that apothem is the radius there. That's a right angle. Where there's a right angle, there is a right triangle. So we're going to work that right triangle here. That's 10. We're going to get that little green piece. Got ourselves a right triangle. We need an angle to work with. So we're going to draw in our pizza slices. You're like, oh no, not this again. That's 360 divided by 6 pizza slices. 1, 2, 3, 4, 5, 6. 360 divided by 6 is 60, which means this little piece here is 30. I could use a 30, 60, 90 triangle, but that only works in special circumstances when you have a 30, 60, 90 triangle. We're going to use SOHCAHTOA because SOHCAHTOA works everywhere. So I need that little X there. This is opposite, this is adjacent. Got an OA combo, which means I'm using tangent. So the tan of 30 over 1 equals what we want, which is this x, over our adjacent, which is going to be the 10, cross multiply. And our little x piece that we need is going to be the tan of 30, whatever that is, times 10. Tan of 30 times 10. We're going to call that at 5.8. Look very carefully. What you have found is only half a side length, 5.8. So we have to double that to get a full side length. So times 2, I'm going to get 11.6 there. If we're going to just double that, 11.6. Now our perimeter, one side length is 11.6, but we have 6 sides. So our total area of our hexagon is going to be 6 times 11.6 times our apothem 10 divided by 2. 6 sides times 11.6 times our apothem, which is 10, divided by 2. And I get 348. To get my area of my shaded region, we simply subtract those two. 348 minus 314.2. And I get my shaded region, which seems very small because it is 33.8. That's my shaded. The ultimate question was not the area of the shaded region. It is what is the percent probability that a point within that hexagon, any random point within that hexagon, what is the percent probability that it lands in the shaded region? So you take the area of the shaded region, which is that 33.8, you divide by the entire area of your target, which is the hexagon, which is 348, and that gives you your percent probability. So if you look here, this is basically 0.097. This is going to round up to 0.1. So there is approximately a 10% chance that any point within the hexagon is going to randomly land in that shaded region. Once again, look at all these steps, and I'd like you to circle which one of these steps might you have overlooked if you were completely on your own. Would you have overlooked making an icon equation? Would you have overlooked one of these equations? Would you have overlooked how to find the pizza angle or the right triangle? Would you have overlooked the equation for probability, which is simply part divided by whole? Which one of these steps I'd like you to identify would you have overlooked if you were on your own? This page you're going to do on your own. Restart the video when you're done. Pause. Okay, let's see how you did here. This was easier. Said find the probability that a point lies in the shaded region compared to the entire circle. So to get the shaded region, you should have done, I'm going to make an icon equation here, basically a square minus, take away 4 of these circles. So area of a square, you should have done side squared. Area of each of those circles is pi r squared of our area, and then you had 4 of them. So your side squared is really simple. That's going to be 6 times 6, it's 36, minus, if you drew the 6 down this way, you would have figured out that your diameter is 3, therefore your radius is 1.5. So 1.5 squared times pi times 4 would give you the area of the circles. There's your radius squared times pi times 4 of them. Should have gotten 28.3 for the circles, and you should have subtracted to get the shaded region, 36. And I've got approximately 7.7 would be the shaded region. 7.7 is your shaded, divided by your entire square, which is 36. And there is approximately a 21% probability that any random point landing within the square would also land within those circles. If you got this problem correct, big star smiley, woo-hoo! If you forgot a piece, write yourself a little note. What are you going to remember next time? Please summarize today's lesson.